Welcome back. Let's talk about Chapter 3, Simple Resistive Circuits. So I have these notes that are posted, and you can print these out and follow along. So most of this is a review from physics, so we're going to go fairly quickly. If you have two resistors in series, you can just add them together. So R equivalent is R1 plus R2, or graphically it looks like this. I have resistor R1 and R2, and the equivalent is resistor R3. So if I had a 1 ohm resistor and a 2 ohm resistor, then the equivalent sum would be 3 ohm resistor. And that should make sense intuitively to you, because a resistor is just a certain length of a material that restricts the flow of electrons. So we have a length of that material, and then we have another length of that material. We just add those two lengths together, basically, and get this. All right, now when you have resistors in parallel, like this little diagram right here, I have a 3 ohm resistor and a 3 ohm resistor. I basically provided two paths for the electrons to go through. So it's easier for the electricity to get through this whole thing. So the equivalent resistance is going to be 1.5, or, well, if this one was 3 and this one was 3, it works out that the equivalent resistance is 1.5 by this formula right here. R equivalent is the sum of the two resistors, or I'm sorry, the R equivalent is the product of the two resistors over the sum of the two resistors. And R equivalent will always be less than the smallest of the original resistors here, because like I was saying, you're providing an additional path. So whatever the smallest resistance was, there will be another path that the electricity could go through, and so the total resistance is less. Okay, typically we deal with pairs of resistance and of resistors in series and simplify them down to the equivalent, but often we can't do that, so we have a more generalized formula for any number of resistors where the equivalent resistance is 1 over the sum of the reciprocals. So the equivalent resistance is the reciprocal of the sum of the reciprocals. So you just take all of these individual guys, if we had more than two, take their reciprocal, add those together, and then divide the whole thing. Okay? The next thing is this idea of voltage division, all right? So if you have a voltage source and then you have two resistors in series, okay, so voltage division applies to two resistors in series, then that voltage will be dropped across the two resistors with a ratio that's proportional to the resistance values. So here I have a 12 ohm resistor and a 4 ohm resistor. So the 12 ohm resistor is 3 times bigger than the 4 ohm resistor. So the voltage drop will be corresponding to that. So here the 75 volts is 3 times bigger than the 25 volts. And these two voltages will sum to the original voltage. So I'm splitting or dividing this 100 volts into 75 volts and 25 volts. And the ratio of 75 to 25 is the same as the ratio of 12 to 4. So the math equation for that is this. So V0, this is just the voltage of interest for this particular little circuit, is given by the source voltage V sub S times this little guy here, R sub 2 over R1 plus R2. And the way I remember this is V sub 0 is associated with R2 in this case. So the thing that you're trying to find here, V0, you put the corresponding resistor on the top. So we're trying to find the voltage across R2, so we put R2 on the top. All right, and so this is equivalent. This is exactly, V0 is exactly equal to this for the case of an open circuit. So across AB here, the voltage across AB, which is really the same as the voltage across R2. AB is an open circuit. That voltage across this open circuit will be exactly this formula here. But oftentimes we will put a load across this, right? We'll put another resistor across these terminals AB. So in this example, AB is an open circuit. which is another way of saying that the load resistance is infinite. But it won't always be infinite. It'll often be some other resistor. So you can still use voltage division to get an approximate value for V0 when you have a load. Okay, and so this is this little formula here is V0 is approximately equal to same formula here, but the tilde, these double tildes mean approximately. It's going to be approximately equal when the R sub L, the load resistor, is much, much bigger than R1 or R2. And by much, we mean at least 10, maybe 10 to 100 times bigger than the V0 will be approximately the same as if it were an open circuit. Okay, so that's a useful thing to know. We're going to look at that. We're going to work at some problems with that. You can think of it as a simple way to make a certain voltage, which I've done on the bench sometimes. Like say you have a 12-volt battery, but what you really need is 3 volts. Then you can select resistors in your divider network to give you the 3 volts that you need over here. And that'll work as long as the thing that you're trying to drive, that is the load, has a very high resistance, much higher than the voltage divider circuit. Okay, now we're going to work problems on all of these in more detail. Right now we just kind of want to go through this stuff. Okay, the analog, or the buddy of voltage division is current division, right? So voltage division applies for resistors in series. We have current division that applies to resistors in parallel. And for current division, here I have 2 resistors R1 and R2 in parallel. This current from the source is going to come to this node here, and it has 2 ways to go, so it's going to get split. So some of the current's going to go this way, and some of the current's going to go that way. And the ratio of the split is proportional to the resistor ratio. So here I have a 4 ohm resistor and then a 2 ohm resistor. So my 30 amps is going to get split 10 and 20. You see the 4 ohm resistor, that's twice the value of the 2 ohm resistor. It's a 2-to-1 ratio. So the current will have that same 2-to-1 ratio, right? The 20 amps is twice as big as the 10 amps. It's just that the 20 amps goes through the smaller resistor now. Okay? So like in voltage division, the higher voltage is in the larger resistor, but for current division, the higher current is in the smaller resistor. So we're going to see these kinds of, analogies, series versus parallel, and current doing this and voltage doing that. We'll see that a lot. Anyway, so in the formula, I1, this I1 here is given by the source current, I sub S, multiplied times this factor here, that R2 over R1 plus R2. And for finding I1, this current here, we use the resistor on the opposite branch. That is, we put R2 on top to find I1, which is kind of the opposite of what we do in voltage division, where we're finding this V0, we put R2. So you put the adjacent resistor to find a given voltage. You put the resistor that's right there, the adjacent resistor. But to find a current, like to find this current, you put the opposite resistor on there. Okay, so voltage division and current division are analogs of each other. I'm using the term analog not in the engineering sense, but in the more general analogous. I said in the word analogous, right? Not in the sense analog versus digital. That's a different meaning. Okay, the next topic is measuring voltage and current. Okay, so we have this thing called the D'Arsonval movement. It's a little gadget that this guy D'Arsonval invented a long time ago. He took a magnet, so there's north and south poles of a permanent magnet, and then he took a little iron core coil type magnet, an electromagnet basically, where you have a coil of wire wrapped around an iron core, and as the current, as you apply a current I sub meter through this coil, so you have to apply a voltage V sub m across the coil to make the current move. But anyway, as you apply V sub m and I sub m, you'll induce a field in here, and the magnetic field will want to align, north to south and south to north. So this little magnet here, which can turn, will align with the permanent magnet as the IM and VM are applied. There's a spring in there that wants to force it the opposite direction, but I didn't draw that because it gets to be too messy. But anyway, then you stick a needle on this thing, and you can use that for a meter, right? As you increase the I sub m and V sub n, then this thing will twist around trying to align because of the magnetic field, and it'll move the needle. So you can build all kinds of interesting gadgets out of this Darson ball movement. So before we look at the gadgets, a little bit more about this meter. What we're doing here is we're applying a voltage across the coil, and that'll make a current flow. That'll induce a magnetic field, which will resist the spring and turn this thing. So there's a lot of weird stuff going on in here, right? There's magnetic fields, there's spring forces, there's all kinds of crazy stuff going in here. The physics is a little bit involved. But in the end, we have Ohm's law, we have V equals IR, right? So a resistance is V over I. So we can take this voltage that we've applied and the associated current, and we'll get a resistance. That is, it'll look like a resistance. So that's what I'm stating here. So the book uses this example movement. That what they mean by that is you could construct a movement. There's many variables, right? You can increase the size of the magnet, the strength of the spring, how many coils of the wire, all of this stuff. But let's say you build one, and it happens to have these particular characteristics. That is, when you apply a voltage of 50 millivolts across this coil, you will get a current flow of 1 milliamp at full scale deflection. That is, when the needle's all the way to the end of its travel. So it's possible to build a meter that has these characteristics, right? A given voltage and a given current will give it a given deflection. If you do that, then there's the resistance of the Darson ball movement, or R sub D, is given by Ohm's law. Basically the 50 millivolts divided by the 1 milliamps, and you get 50 ohms. So what I'm saying here in kind of a roundabout way is that the meter appears to have a resistance. It looks like a resistor by Ohm's law. Okay? By the voltage divided by the current, this thing looks like it's a resistor. But there's a lot more than going on in there than just simple resistance. Okay? That's our model, right? We can pretend that this thing is a resistor. We're going to model this with a resistor. But it's much more than a resistor. It's a lot of weird physics going on in there, but that's an important modeling concept. Okay, so we're going to model this Darson ball movement with a resistor and have the value R sub D. Okay, doing that, we can build a couple of gadgets. We can build something to measure current, we call an ammeter, and something to measure voltage called a voltmeter. So here's how you build a voltmeter using a Darson ball movement. So I've represented the Darson ball movement with just a resistor with the value R sub D resistance on it. So you can take another resistor, sometimes called a shunt resistor, and put it in parallel with the Darson ball movement, and you end up with this guy here. And the purpose of R sub A, this shunt resistor, is just to limit the current through the movement, because anything more than 1 milliamp on this movement here will toast it, right? So you're trying to measure some current going through this meter here. You're trying to measure a current that comes into this meter. You want anything more than 1 milliamp to go down through R sub A. Okay, so R sub A limits the current through R sub D. Okay, so we want to use small values for R sub A because ideally we want an ammeter to look like a short circuit. We don't want it to affect the circuit at all, right? We want it to appear to be just a wire. So to do that, we use small values of R sub A. Okay. Okay, we can also, using this D'Arsonval movement, we can construct a voltmeter. And you do that by taking a shunt. I'll call it a shunt again, although that's not, there's a better term that escapes me at the moment, but take your D'Arsonval movement, which we've represented with a resistor with value R sub D, and put a shunt resistor R sub V in series with it. And the purpose of R sub V is to limit the voltage across the entire meter, because this little D'Arsonval movement can only handle V sub M. Any more than that and it'll get fried. So you put R sub V in there to take most of the voltage, and then whatever's left will be no more than V sub M. Okay, and so R sub A limits the voltage across the movement, right? R sub A, this should be R sub V. R sub V limits the voltage across the movement. It'll take most of the voltage. So this is like a voltage division problem in here, and this is like a current division problem in here. Okay, so that's why this stuff is presented in this chapter, really. There's other reasons why it's in here, but that's one of them. So overall, we like to use big R sub V values because we're trying to make this voltmeter appear to be an open circuit to the circuit that it's measuring, right? We don't want the meter to affect the circuit. So we use very high resistance values. So it says this meter altogether will be approximating an open circuit, right? Which is sort of the analog to an ammeter approximating a short circuit. So in our ideal model, we try and get this to look as much like a short circuit as we can, and we try to get this to look as much like an open circuit as we can. That's ideal. In real life, meters will affect the circuit, okay, especially a D'Arsonval movement, which is going to have a significant effect. Modern day digital meters use other devices to take the measurement, and they are much closer to ideal than a D'Arsonval. But this is good stuff for learning the basic theory of circuits. In real life we use modern equipment and computers and all kinds of stuff, but yeah. So that's measuring voltage and current using a D'Arsonval movement. Just to review this, there's a lot of good stuff in here. One idea is that we're taking a pretty complicated gadget with a lot of weird physics and simulating it with a resistor. That's one idea. And then we can take that movement, the D'Arsonval movement, and construct either a voltmeter and an ammeter. One of these devices, this one, is like utilizes current division, and this one utilizes voltage division. And also we're approximating some ideal short circuit and open circuit things. So just to summarize what I said. Okay, the last page is another couple of concepts. One is Wheatstone bridge. So this guy named Wheatstone, which I'm assuming, it's an interesting name, Wheatstone. I'm assuming somewhere in his family they were millers. I'd imagine that they had those big stones that they used to grind wheat or different grains. But I don't know. I haven't researched it. But anyway, interesting name, Wheatstone. So this is a device. A Wheatstone bridge is a device for measuring resistance. So you have to have some known things. So you have 3 known resistors, R1, R2, and R3, and you buy these at the at the high quality resistor store, you know, down at the fancy mall or wherever you get those, on Amazon, I don't know. But these are R1, R2, and R3 have to be known to a high degree of accuracy. Okay, and R3, this little arrow means that R3 is adjustable. So what you do is you adjust R3 such that there's no current flow across this Darsenball movement. I represented that by showing the needle pointing straight up, which you would have to construct a meter to have this behavior. But basically, you can put a meter in there and adjust R3 so that there's no current flow. And when there's no current flow, it basically means there's no voltage potential across this. So now I'm skipping a little bit, but what that leads to pretty quickly is that the voltage across these two nodes here is the same for both branches. So that leads to this. That is the ratio of these two guys is and the ratio of these two guys is the same as the voltage across here. So that the derivation in the book is a little more precise than that, but basically it comes down to this thing, which is mostly what we need. Basically, the unknown resistor R sub x is given by these three known resistance values after you've adjusted R3 to get zero current through here. All right. So what about the modeling part, right? So this thing will work for resistors in a certain range, 1 ohm to 10 mega ohms. Okay, below which and above which you're going to get some significant heating effects that are going to throw off the measurement. So that's where the ideal part of it breaks down. Below and above, like at some point these guys will get too hot, in which case the resistance is no longer straight line. And then at another point, the current's going to be so low that a lot of it's going to leak out. You know, electrons leak through stuff. You know, they tunnel through stuff. There's quantum effects that are going on, and these quantum effects are only noticeable at very, very low, values. Like for power transmission, you're dealing with gigawatts or whatever. You're not going to see quantum leaking. You're going to see other kinds of leaking, but not quantum leaking. But for the opposite end of the universe, like a microchip, where you have very low levels of current now, they're trying to reduce the power use in chips, right? So they're reducing the voltages and reducing the current flows. So the current is so low that tunneling effects start becoming significant. Electrons just leaking out by, doing weird quantum stuff, disappearing and reappearing on the other side of things, and all kinds of crazy stuff. Anyway, so just to talk a little bit about the idealness of this thing. The last thing is delta to Y and Y to delta equivalence. So let's say you have three nodes, A, B, and C. You can connect those three nodes with three resistors in two different ways, right? These three nodes, you can connect the three resistors in a Y configuration like this, or you connect three resistors in a delta configuration like this. Okay, you can transform back and forth between these. That's useful for circuit simplification. It's useful for circuit simplification, but it's also useful for these kind of connections happen in AC power circuits all the time. So it's useful for looking at those guys. But anyway, given one of these, we can convert it to one of these, and given one of these, we can convert it to one of these. Okay, so if you're given a delta, if you're given this configuration with resistors A, B, and C, you can find the equivalent R1 value with this formula here, right? So if you know RA, B, and RC, you can plug that chunk into here and get R1 for the equivalent Y. Likewise with R2 and R3. So look at these formulas. The denominators are all the same. The numerators differ in that they're missing the analog companion of resistors. In other words, RB and RC are on here. RA is missing. And RA is you could say, corresponds to R1. Okay, and here RB is missing, so we put 2 here. And here RC is missing, so we put 3 here. Okay, likewise we can go backwards, like given a Y configuration, we can calculate the equivalent delta configuration with these 3 formulas. So given 1, 2, and 3, we can find RA by using this stuff here and all these others. And let's look at these 3 formulas. The numerators are all the same, and the denominator consists of the analog to what you're trying to find. So if you're trying to find RA, then R1's on the bottom. If you're trying to find RB, R2 is on the bottom. And if you're trying to find RC, R3 is on the bottom. All right, that's the basics summary of chapter 3. I went kind of quick because it's mostly a review. We'll go through the problems, several problems involving each one of these things in detail. Okay, see you next time.